That's how we define the logical operators. Well, in this class, you'll call these logic gates, okay, which is just another name of doing the same thing, except the word gate applies to circuitry inside the processor. And then we have one more thing. We got X versus not X. X is Boolean or binary. It can only be 0 or 1. When X is 0, what is not X? 1. When X is 1, what is not X?
0.
0. Okay, we have defined every single logical operator that we'll ever need in the class. Because everything else can be derived from these three. In fact, out of these three, one is redundant. The negation can never be redundant, but one of the and or the or is actually redundant. In other words, if I don't give you or, you can actually use and not to come up with or. If I don't give you conjunction, you can use disjunction and negation to come up with the other one, the one that's missing. Yep.
What about exclusive or?
Exclusive or can be done with these two. Okay. You pick negation of one of the other two. You can come up with all the possible logical operator that you ever need, or that it can ever exist. Okay. All right. I don't believe you. In my classes, I always train and tell my students, don't trust me. Okay. How many people still remember that from cisp310? Very good. Okay, so never trust me, and you always ask, but I don't think so, right? So let's try this on this mystery operator here. Okay, so somehow my input looks like 0, 0, and the output has to be a 0. If my input is 1 and 0, I want the output to be 1. If the input is 0 and 1, I want the output to be 1. If the input is 1 and 1, I want the output to be 0. How can I make that happen? Using only conjunction, disjunction, and negation. That's the question. Well, this one is actually harder. Let's look at the next column first. The next column is like pretty easy. If the input is 0, 0, I want a 0. If the input is 1 and 0, I want a 0. If the input is 0 and 1, I want a 0. When the input is 1 and 1, I want a 1. Have you seen anything like that?
X and Y.
X and Y, exactly. So the carry, okay, the carry of X plus Y in binary is really just X and Y. X being binary and Y being binary. Is that making any sense to you? Because if you look at this column, which is the carry of adding two binary digits, 2 bits, it is exactly the same as the AND function. So we can just go ahead and say, oh, if you want me to tell you the carry of X plus Y, X being binary and Y being binary, I can just use conjunction to give you that answer. Is that making any sense? Okay. So in electrical engineering and also computer engineering, we know exactly how to make AND gates to happen. Okay, we know how to make AND gates inside the processor, so we got this one handled. So the next question is, how do we deal with the partial sum? Okay, this part here is called the partial sum. This column is called the partial sum. The partial sum is a little bit harder. Okay, so let's try to see if we can find out how to do the partial sum here. So I'll just do this is my partial sum. And we have to shift everything. Should have used a spreadsheet to do this. All right. So now the question is, how do we express the partial sum? The partial sum of X plus Y is, what? What do you think? Now that we know what is AND, what is OR, and what is not, is there a way to arrange things so that the output will match the partial sum exactly? Well, I didn't say it was easy.
First,
Yep.
not and.
You actually need to group things. It's going to be a little bit nested. So I'll give you the answer. Okay, I'll give you the answer, and then you guys can help me verify the answer is actually right. Okay, so the partial sum is this. It is x and not y, or not x and y. Okay? Which also turns out to be exclusive OR. That's also known as exclusive OR. Okay. I look at this long and clumsy expression, and I'm not 100% convinced that it is the same thing. It will give us the same partial sum as the other column. So how do we check it? Or do you want to take my words?
The ones and zeros.
You never take tax words, okay? You might take another professor's word and be okay, but you never take my words, for example. Yep.
Test the zero and one.
Exactly, we can test it. The nice thing about binary stuff is it's easy to test. Okay, there's a finite number of combinations, so you can enumerate and test everything and prove that it is actually correct. Okay, so we'll go ahead and try to prove this. So the way to prove it is to say we got two independent binary variables. Okay. So we'll work on this one really step by step. What happens when x and y are both zeros? All right, so that means x is 0, not y is 1. It means not x is 1 and y is 0. Is that making any sense? I'm working with the innermost part of the parentheses. All right, the next step is to do the conjunction. 0 and 1 is what? 0. 1 and 0 is 0. And then finally, we move all the way out to the OR. What is 0 or 0? 0. Oh, okay. That seems to work out okay because the input is 0, 0. The output is 0, which matches this 0 here. Okay, we got the first row done. Then we move on to the next one. We move on to 1, 0. Okay, x is 1, y is 0, so not y is 1. X is 0, excuse me, x is 1, so not x is 0. Y is 0 to begin with. 1 and 1 is 1. 0 and 0 is 0. 1 and 0, 1 or 0 is, 1 or 0 is 1. Okay, very good. So I can add a little separator here just so that it's clear, what we're dealing with here. Okay. Does everybody understand how to read this? Okay. I'm just making an expression tree, except using just text. All right. The next combination is 0 and 1 as input. Okay, so we have 0 here, 1 here. X is 0. Y is 1, but not 1 is 0. X is 0, not x is 1. Y is 1 to begin with. What is 0 and 0?
0.
What is 1 and 1?
1.
What is 0 or 1?
1.
1? Oh, that works out too, right? Because my input is 0, 1, my output is 1, which matches this mysterious operator that is required to output a 1 when the input is 0 and 1. We only have 1 to go, so we only got one last chance to prove tag wrong. What do you think? Is that a good chance? All right, so the last case is 1, 1. Okay, x is 1, y is 1. If x is 1, x is 1. If y is 1, not y is 0. If x is 1, not x is 0, and y is 1. So now we have 1 and 0,
0.
is 0. And we have 0 and 1,
0.
which is 0. And then we have 0 or 0, which is 0. Okay, the input is 1, 1. The output is 0, which matches this row also. In other words, instead of using the arithmetic interpretation to come up with the partial sum column, I have just converted the whole thing to use just logic gates, and, or, and not. Okay. Is that significant, or is it just, oh, you're just showing off, these totally useless stuff that we are learning in this stupid class? Why is that useful, if it is useful?
Translate into the transistors, turn them on.
Exactly. So we have just translated something that is arithmetic into something that is just purely logical. Okay? So that is why this is actually a very significant step, because now we know how to make processors and other chips to perform, this is a partial addition. Okay, it's not the whole thing, but we are getting there. Okay, any questions about this? No questions? Any question about the significance of this particular step? No questions? How many people here are on their track to a computer engineering or electrical engineering degree? Okay, so this stuff is particularly important for you guys because that's you're mostly working with the logic gates. Okay, computer science people typically don't have to drop down to this level. In terms of programming, we don't have to deal with the logic gates like this. All right. Well, this is really cool because we just finished binary addition, and we have just done this part here. So the term half adder refers to the fact that two half adders are required to perform a full adder to form a full adder. A half adder has two inputs and it has two outputs. Each of its two outputs corresponds to a value to be added. One of the two outputs corresponds to the result of the adding, which is the R, which is also the partial sum in the text editor. The other one corresponds to the carry of the addition, which is the C here. Okay, so this is really just a much more concise way to represent what I put into my text editor here. Okay, so if you look at this stuff here, it's really the same thing as this stuff here. Are we doing okay so far with that? And then the rest is, it is not difficult. I guess, once you understand this, it's not difficult to see that the equation of C is xy. Now, this part requires a little bit of explanation. The reason why it is expressed as xy instead of x and y is because in Boolean logic, the concept of conjunction is equivalent to multiplication. So when I say xy, it is kind of like saying x times y. And that's why it is just expressed as xy. Is that okay? So this is a notation thing. Multiplication is quote-unquote equivalent to conjunction. What about the other one? It's even more, kind of cryptic, because this is the result or our partial sum. I use, xy prime plus x prime y instead of this expression here, x and not y and not x and or, excuse me, x and not y or not x and y. Well, that's because the multiplication is implied and it is conjunction. The prime is the negation, and then the addition is the or. So that's just a shorthand, so you don't have to spell out and or and not. Instead, we are just using these symbols to represent conjunction, disjunction, and negation. Just a notation change, but otherwise it has the same meaning, exactly the same meaning as what we talked about earlier.